Hello, I'm Dr. Patricia Shaw, and welcome to our series of short videos to give you a brief introduction to various robotic principles that can be explored as part of the challenges available on the robot benchmark. As part of this series of videos, I'll be covering I'll first of all be introducing what Robot Benchmark is and how to get started in it. And then in each of the videos, I'll be looking at the robotics principles that are covered by each of the challenges. I'll give a review of the starting programs that they provide for the challenges, and then look at hints and tips for how to go about solving the challenges. I should say we're not sponsored or supported by the Robot Benchmark, and it's not a tool that we provide directly, but we do see it as a useful way of introducing the principles using a relatively easy to use online tool. So, what is Robot Benchmark? Well, first of all, it's an online, web-based simulation of various different robots with different challenges set involving those robots, and they're simulated in a 3D environment. So robots need to be able to sense and act in an environment, and therefore they need to be embodied and situated within that environment. The Webot simulator, which the robot benchmark is based on, provides a variety of tools to simulate robots and environments, and that can really help to speed up the testing and development of programs. Webots is a free and open source tool, meaning that anybody can actually contribute to the development of the simulator, and anyone can freely use it for non-commercial applications. If you are interested, then you are able to download and install the Webot simulator on your own computer. However, for the purposes of this series of videos, we'll be using the online version, which is just focuses on a subset of robots with a set of predefined environments and challenges to be able to do that. And that doesn't require any installation or setup on your part. It does, however, provide a set of challenges that can be used to compare the performance of your programs against other people's programs. There's a scoreboard where you can compare your speed of achievement or how accurately you're able to complete a challenge to compare it against other people's approaches. It is, however, worthwhile saying that individuals' code for achieving their results is kept completely private. So you can compare how well your particular algorithm performs against others, but you can't actually see the other people's algorithms to see how they did it. And the final thing to say is that it uses the Python programming language. So you can, it provides example programs to get you started, and then you can modify those programs to improve the performance of the robot for each individual challenge. Now, before we go too much further, it's possibly worth saying a little bit more about what Webots is. And specifically, it's actually a middleware system that sits between the program that you're writing and the robot that you're controlling. Quite often in the sort of robotics that we do, we're programming the robot directly. So we might be talking directly to the motors and specifying how fast that motor should turn. But when we have a robot middleware, we can actually, the middleware itself will provide a level of what we call abstraction away from the physical hardware, which means that we can actually take a single program and apply it to lots of different robots. So any robot that has wheels and is able to drive around, you could take the same program and it would work very similarly on each of those robots without having to modify your code. That significantly increases the reuse and the ability to share programs with one another. And even more than that, robot middleware software tends to provide a lot of libraries that people can reuse for solving common problems that we encounter as developers when writing programs for robots. And those libraries tend to be really well tested so that you can be confident that they're going to work how you want to, so you can then focus on the more interesting parts that are specific to your application. Now, Webots isn't the only robot middleware out there. There is actually quite a few out there, but I'm just mentioning two here today. And the other one I want to mention is the Robot Operating System, commonly known as ROS. It has simulations and it has libraries, much in the same way as Webots. And there is a tool, the Construct Sim, that does provide some online simulation of it. So if you are interested, then that might be an alternative that you can go and have a look at. But as I say, in this series of videos, we will actually be concentrating on using the robot benchmark, which is based on the Webots simulator. So let's have a look at benchmark a bit more closely. Now you can access the robot benchmark through a web browser. They recommend Chrome, Firefox, or Opera as the main browsers. On Windows, they also support Edge and IE, and on Mac, they support Safari. If you are using something else, then there's a good chance it will actually work. It does work in pretty much all the browsers I've tried it in so far. But if you are having any problems, then possibly switching to one of the recommended browsers might help. And you can find it by going to robotbenchmark.net. Now, you don't have to have an account in order to be able to use it. You can use it for without creating any kind of account whatsoever. But it is recommended that you do create a free account to be able to use it. And that simply means you'll be able to save your progress, and you'll also save the programs that you write as you go along. So you can come back to them and carry on working on them at a later date. It also means that you can record your scores on the scoreboard, and so you can compare your performance to others. And I'll have a quick jump over to the robot benchmark to have a quick look at what it looks like. So when you first come to robot benchmark, it will look something like this. You can scroll down and you'll see the various different challenges listed at the bottom. It recommends in green which ones to do next, and you'll see stars listed alongside each of them. And the stars indicate the level of difficulty. As part of this series of videos, we'll only be going up as far as the 3-star video, so we'll be covering the first 8 challenges there. But if you are interested, then you are more than welcome to carry on, and we might add some extra videos later on. But initially, the focus is on the first 8 videos. As say, you can actually sign up for an account at the top, and then you can log back into that. All it is name and email address, and they do promise not to share any of your details elsewhere. So it is literally just to be able to record your results. And if we have a look at the first of the challenges here, you can see the scoreboard of people's performances at the bottom there. When you are looking at these, then it does give you a little bit more detail about the challenge itself. So what robot it's using, the level of difficulty, and some indication of how long they might expect you to spend on this. So as a quick overview, as I say, we'll be focusing on the first 8 challenges, and it gives you an idea of what robotics topics each of those challenges are covering. But as I say, we'll go through each of these in turn. But to start off with, let's have a look at the first challenge. Now, this challenge is all about familiarizing you with the simulation environment and how to move around and change the view within that environment. You can have a look at how the simulator works and the information it provides you in there, and how the assessment of your performance is actually done with the metrics. So let's switch back a moment. So in order to get started, let's start on the first first benchmark. So when you load it up, you'll have this information panel in the top left corner. It gives you a brief overview of what this particular challenge is. You then have a metrics tab, which tells you what the objective is to actually be able to achieve. And in this case, if we scroll down, what the objective is to try and get the view to appear as this image showing at the bottom. Up at the top, it will show you a percentage of how close you are to achieving that. So if I currently just move the view around a bit, we can see that number changing. And then it tends to give you some instructions about how to do the moving. So left clicking will drag, and then dragging will rotate it. If you are using a trackpad, then it's a little bit more awkward. But if you're using a external mouse, then it's slightly easier. It can still be done with a trackpad, and actually I'm using a trackpad here. So 2-finger clicking is dragging it around. Left clicking is changing the rotation around where I'm actually clicking. Right click, scrolling up and down changes the zoom in and out. And so we can try and rotate this around and see if we can get it a bit closer to what we want it to look like there. I'm not going to try and get it 100%. I'll leave you to have a go at doing that yourselves. But we can get it a little bit closer to what it should look like. And if we have a look, then currently I'm at 57.8%. So not too far off, but it could obviously be much better if I spent a few more minutes trying to improve that. When you're done, you can click on the record there, and if you are logged in, then it will show your score on the scoreboard. It's worthwhile being aware of some of the other details here. We'll have a look at some more of these, but there is a user guide down here. And we'll have a look at these other buttons next. I'm just going to go back to exit out of the simulator, and then we can go back to the benchmark list. So the second challenge is where we start to actually get on to some programming of the robot. But again, this is mainly about introducing the programming interface, introducing some of the controllers for controlling a robot, and starting to actually get you thinking about how robots actually move. So before we go too far with that, let's have a look at different types of control mechanisms or configurations for robots driving around. And we have 4 main different types of wheel configurations that you tend to come across in robots. Some more common than others, depending on the size and complexity of the robot. So the first of these, perhaps of the larger scale robots, is what we call Ackermann steering. And this is where we have 2 front wheels are connected together by a sophisticated axle. And actually the way we often compare these steering mechanisms is by looking at where the center of turning circle is for that particular configuration. And in this case, where we have a 4-wheel vehicle, then the center of turning circle is aligned with the rear axle, and the angle of the front 2 wheels is coupled together and controlled by a single steering angle to maintain that center of turning circle angle. You may actually recognize this as the type of steering used in cars and vehicles on the road. So it's quite common for larger scale robots, but perhaps not quite so common for small scale, perhaps the hobby scale robots that we're more familiar with. In this case, there tends to be what we refer to as differential drive. And in this case, we tend to just have 2 wheels that are powered. They're fixed in terms of their alignment to the robot, but we control each wheel independently. And that means we can send a different speed of turning to each wheel. So instead of having the center of turning outside of the robot, the center of turning actually tends to be in the middle between the 2, on the axle in the middle between the 2 wheels, so we can turn on the spot potentially. And that's quite commonly used in small-scale hobby robots. Going back up to the larger scale robots, we have something called skid steer, and this tends to be more like your tank driving mechanisms. So in this case, we have a series of fixed wheels or tracks that we can control the speed of, and the center of turning is much more dynamic. It's not fixed in a single location. But by changing the speed of the two sides, it ends up dragging some of the wheels around, which is why we call it skid steering. And more recently, you may have come across or started to see some omnidirectional robots. And that's where the type of wheels, often mecanum or omnidirectional wheels, are able to travel sideways, forward, and backwards, or diagonally. So they can travel in pretty much any direction. And it's quite fun to watch, but it's certainly much more flexible. So the particular configuration of the wheels is referred to as part of the kinematics, and that describes the size of the wheels, the lengths of the joints between the links between the wheels, and how those joints or wheels actually turn and rotate. So that's the kinematics of the robot. What we then have is our controllers, which describe how we actually go about controlling those joints. And quite often we use something called either position or velocity control. In the case of position control, we're specifying what angle we want that joint to turn towards. And so we can give it, say, turn to 180 degrees, and it will rotate that joint to that particular angle. It is worth noting that actually when we're dealing with angles in robotics, inevitably we're actually using radians rather than degrees. So that would be pi radians instead of 180 degrees. But we can also use velocity controls, so instead of specifying a particular angle, we can specify a angular velocity, or how fast we want it to be turning at, in a particular direction as well. And if we want our robot to drive a certain distance, then we could tell it to stop after a certain duration. There are other types of control, such as force torque, which is often used, particularly if we need some feedback to the robot and want to make sure that our robot's safe around people. Then we'd perhaps use something more like force torque. But most of the types of robots we'll deal with here are position and velocity controlled. And then in terms of the way in which the robot control is handled, we have what we call open and closed loop control. In the case of open loop, then we will tell it what to do, and we're not too worried about getting any feedback or responding to any feedback based on how the robot's performing. But in closed loop, we do have some kind of feedback that's then informing what new commands we send to the robot. But we'll cover more on that later. What I will say, though, is that as the robot is driving around, we want to be able to know how far it's travelled. And actually, by bringing together the kinematics, so the configuration of the robot, the size of the wheels, the velocity or the position that we're tending those joints to, we can actually start to build up some idea of how much the robot has moved from its starting point to where it is now. And that's called the odometry, being able to calculate and track how far we've moved and in what direction. And using that, we can actually start to build up a map of the robot driving around. So let's have a look at this first challenge in a bit more detail. This is using the Thymeo 2 robot. And that robot is a differential drive robot with 2 wheels. The wheels are of radius 21 millimeters. It's quite a small robot, about the size of a robot vacuum cleaner, if you've seen a robot vacuum cleaner at all. And in this particular exercise, they simply want you to use the information about the size of the wheels to get the robot to travel a set distance. So they're using, in this case, a position controller for the wheels. which is actually quite unusual. Normally we'd use a velocity controller for the wheels because we're more interested in how fast the wheels are turning rather than how many rotations they're making. But the position controller is actually the simpler starting point. So for this first challenge, they're using that one. But they do want you to think about the wheel kinematics slightly. So if we want the robot to travel a set distance and we know what the radius of the wheels is, we can actually calculate how much we need to rotate the wheels by in order to get it to travel that distance. And that's using this equation here. That might look slightly overwhelming at first, but it's not actually too different to anything you may have come across before. So if we know the distance traveled, or we want to know the distance traveled, then we can supply an angular rotation, how much we want to rotate the wheels, and this is the position that we're giving to the wheels. And we know what the radius of the wheels is, so we can use this to be able to calculate how far we actually want how far the robot will travel for a particular rotation. Or if we rearrange it slightly, so some of you might be familiar with the equation triangle, we can use this to be able to calculate a distance. So let's switch back to Robot Benchmark a moment and have a bit more of a look at this robot programming challenge. So again, they're saying possibly just a few minutes for this particular challenge. Okay. So again, we have the metrics if we want the robot to be able to travel to this distance with a program. They provide some instructions on how to do that. And this is where we get a bit of explanation and details about the actual configuration of the robot. Now, if I right click on the robot here, we get a short pop-up menu, and one of the options on there is to edit the controller. And this is how we actually get to the program that will be running on that robot when we press play. Now, if you do want a bit more help on what any of this means, then you can actually get access to it from the help menu. So there's a question mark in the bottom right corner. And there's a link to the WebOps reference manual here. Now, most of what you want to know will be inside this nodes and API function, and you'll want to scroll down to robot in here. There's quite a lot of information in here, and most of it we won't need straight away. But where the robot has it, you can get access to different types of sensors in there. Here we're using the motor, and it gives you some examples. Specifically here, we're doing it in Python. And you can find out some of the functionality linked to that and how to go about using it. But as I say, they give you a starting program here that you can then modify in order to be able to solve this. So let's have a closer look at what this program is. The first thing it's doing is importing this controller from the WebOps libraries for the robot. And we've also got some Python sys library imported, and they're using that to produce a standard error message later on. So if you want to print out information, much like you would with Python, you can use the standard print approach for printing out messages, or you can use the sys error message to have a slightly different formatted error message in there. Now, in this particular program, they're specifying the target for how far we want to try, and they suggest an initial starting value in there of 10. We're getting a reference to the robot that we want to be able to control, which is this particular robot that it's running on. And then down at the bottom here, it's getting the motors from that robot, and those are referred to as motor.left and motor.right, so we can get access to each motor individually. And then it's in position mode, so we can set the position for that motor to the target that we've defined up at the top. I'm going to save that program with just the 10 as a starting point in it. And I'll pop that back to metrics so we can see. Now we then have some controls down here at the bottom. We have a console where we can see those messages that will be printed out by the program. We have a timer saying how long the programs run for. We've got the start simulation, perform one simulation step, and then reset the simulation back to the starting point. So I'm going to press the play, and there we have it. It moved forward, but it didn't quite get all the way to the target location, and so I would get a score of 83.25 for that. You can see it's not quite gone as far as we want it to go, but the clock is actually still running down here, so I can pause that. I can also reset it back to the starting point in order to get it to try again. So I can go back in, edit the controller, perhaps try a different number. I'm not going to give you the exact answer to this, but you can try different numbers in there, or you can have a go at calculating it. See, that's actually much closer, 99.92%. So I can go ahead, and that will actually have saved that score there for me as well. And to exit, you just press the power button in this bottom left corner. So there you go. That's the first two challenges from the robot benchmark. In the next video, we'll be having a look specifically at the obstacle avoidance challenge. So see you next time.